So, welcome, ladies and gentlemen. It's a great honor and a pleasure to be here and to announce this lecture here. This is a master class, and Nicola Armaroli, I can honestly say, is a good friend of mine. We actually met some months ago, some years ago. We had a fantastic discussion here last year at Trieste Next. It was 2 years ago, actually, at Trieste Next. We had a discussion with a philosopher, and we were talking about energy, environment, and impact of the energy consumption on the environment, also with some, let's say, connection to the shortage of water, shortage of food. A very interesting discussion at that time. So we are going ahead into the direction of focusing on multidisciplinary fields, and the energy environment is one of them. And actually in this direction we are setting up also at this University of Trieste a center, a competence center. Is an interdepartmental center for energy and environment, and into this direction, into this track, this event and other events that have been done recently are perfectly in line. The new challenges of the world are, all of them are multidisciplinary, and energy environment is certainly one of them. So really, again, it's a great pleasure to welcome you here for this this lecture. Vanni, perhaps you want to say something, or afterwards, perhaps. It's up to you. Afterwards. Okay. So you perhaps can say something about the Giacomo Ciamician Center for Energy and Environment.
Well, let me say one thing.
Okay. Go ahead. Go ahead.
Okay. I thank you very much, the rector, for remarking a number of things that are very important, like the foundation of this new initiative. This lecture today is part of these initiatives, and it's interesting because we dedicated this initiative about energy and environment to Giacomo Ciamician, and it's really not a chance that we have Nicola Armaroli today here. He got his education at the Giacomo Ciamician Center department in Bologna, where Giacomo Ciamician got his education and all his career. He spent all his career there founding a fantastic school on photochemistry. And he became the father of solar energy thanks to his vision. So we have, in some sense, a grandchild of Giacomo Ciamician here today, a grandchild in the academic sense, of course. So we're very honored to have one of the main experts on photochemistry and photophysics. His CV is astounding, like numbers are crazy, like more than 180 papers published, H-index well over 50, 9,000 citations and counting. So, but beyond being a scientist, Nicola is also a communicator. He's written a number of books, along with Vincenzo Balzani, who's also a very famous communicator in the field of energy and environment. And so there is really no better person today to talk about this topic, the transition to a sun-powered world, than Nicola Armaroli. Thank you very much for coming.
Thank you very much, Vanni, for this presentation. I'm very honored to be here this afternoon. And I thank very much the Magnifico Rettore for the introduction. And the idea today is to talk about the energy transition and to see perspectives and to see what's going to have in the future, and what probably we have to face, which is a very difficult challenge. And most of you, particularly the youngsters, are going to be strongly involved in this. So I think that everyone has to be aware of what's ahead of us for in the energy transition. So I will in 1 hour I will not have the time to discuss a very extensive topics like energy, of course. So one of the references is this very recent article I wrote with my good friend Vincenzo Balzani, because still from time to time we disturb each other about energy, we discuss, and from time to time we decide to write something as this review that you can download for free, even though you are not a subscriber, because it was in the first issue, so it is downloadable for free. Chemistry European Journal last month. I released an interview on Chemistry Views, which is the online journal of Wiley VCH, in which I also gave some hints about this review, and something that I also going to tell you about this afternoon. So my lecture is split in 3 parts. The first one I will discuss about the status, and then the perspectives, and finally I will focus on the bottlenecks, which are very important and often very overlooked in the energy debate. So let's start from the status. Deciding to what to tell you this afternoon was difficult to talk about the status, because there are many things regarding the status. So I selected just a few topics, and I will give you just some very limited hints. The first one, this is the lecture. This is the slide I typically start with in my lectures. It is the energy timeline. Because as people living in the 21st century, we have to be aware that the energy consumption in the history of our civilization, that dates back to about 5,000 years ago, has been very limited for millennia. And energy came from humans, animals, fire, and wind, basically. But suddenly, about 200 years ago, something changed and started the massive exploitation of fossil fuels. And then within a few generations, our energy consumption skyrocketed, jumped to the sky. And still, more than 80% of our energy supply comes from fossil fuels. 1 century ago, it was 90%. So we didn't make such a big progress in 1 century. So it is still more than 80%. And the big question that we have, everybody is aware of that, is what's next? Because it is pretty clear to everyone that we cannot continue to be up here in this regime using fossil fuels due to climate reasons and due to the availability itself of the fossil fuels. This diagram shows us that we are running very fast, but to give you an idea of how fast we are running, I'm going to give you some numbers. Every year we consume about 10 gigaton of fossil fuels that we extract from the earth. And it can be estimated that the amount of paleobiomass of millions of years ago, of this epoch here, that was needed to make this accumulation of fossil fuels in selected regions of the world, which had specific geological conditions, and particularly in the Persian Gulf, for example. The rest was just widespread all across and was lost in the Earth's crust. Approximately 50,000 gigatons of paleobiomass was needed to sum up all of this. And this amounts at the current level of net primary energy production to 500 years of photosynthesis. So in short, in 1 year, we are consuming half of a millennium of photosynthesis of millions of years ago. So we are clearly running too fast in consuming this energy treasure. There is no doubt that the last 100 years was a fantastic age. We won a sort of lottery living in this period of the history, because we have a lot of energy available to us, and now we can feed, in principle, more than 7 billion people. That was considered impossible a few decades ago. We have access to healthcare. We live in comfortable places, houses, both in winter and in summer. We have a good quality of life all across the lifespan. We have access to education, and we can virtually travel all across the planet within 24 hours, going anywhere. So clearly this was possible due to human ingenuity, but the real engine to this was the availability, the huge availability of fossil fuels that I showed you in the previous slide, that big spike over there. However, fossils will be impossible to replace. And there are chemical, physical, economic, and geological reasons that shows that this era, it is a one-time event in the world history. So this is going to finish sooner or later. And they are impossible to replace. We cannot replicate this energy age in the future. And a paradigm shift is needed. So everyone knows the paradigm shift is shifting to renewables. And the first question that we have to ask to ourselves, do we have enough renewable energy fluxes to power our civilization, our present modern civilization and the future one? And the answer is yes. So this is good news, because if we take one as a reference, the gray cube, as the reference energy, primary energy consumption, the big cubes is the theoretical availability that nature gives us in terms of these energy sources. And the smaller cubes in front of the big ones is the amount that is technically, economically, and ecologically exploitable now. And if you make the summation of the small cubes, you get more than one. So it is in principle possible to shift to a renewable powered world in principle tomorrow morning. But one can ask, why don't we do it? This is obvious. Energy transitions are very complicated things, and the previous energy transition in human history from wood to coal, from coal to oil, lasted decades. And this one will last even longer, because the energy system is a huge machine that is spread all over the world now. But we can do it. We can make it. So that makes sense that I continue in this lecture, otherwise I could stop here. But we have to be practical. I showed in the previous slide primary energy sources, but we are consumers, we are people using final forms of electricity. And what we need at the very end is two forms of energy, electricity and fuels. And presently in the affluent world, the share of final energy consumption is 1/4 electricity and 3/4 fuels. And from these numbers, you can realize how imbalanced is the energy debate, the public energy debate. Because typically when you hear about energy on the media, they discuss about photovoltaics, nuclear, wind. That's okay, that's important. But it's still 1/4 of our final energy consumption. We need much more of this at present, in the present energy system. We have, I have argued somewhere else that we have to shift more and more to electricity, and there are good reasons to do so. However, now the situation is this one. And there is a key difference between these two forms of energy. Electricity is very easy to transport, very easy, in a clean way, silent, quick, but it is extremely difficult to store, and this is a big problem. On the opposite, fuels are complicated to transport, sometimes very dangerous to transport, but they can be stored for an indefinite period of time. So in a way, they are sort of complementary forms of energy, but we need both. So fuels will be needed anyhow, always, because they are so useful and so convenient to use. So another point I wanted to highlight in this first part is that we are in a specific period of the fossil fuel era, which is the twilight period of conventional easy fuels. I'm not a geologist, but so if there are geologists here, please pardon me. What is conventional oil? It is the oil that we have studied at school typically. The oil that you drill, or the gas that you drill, and automatically the oil and gas comes out spontaneously, because the pressure in the reservoir is so that this is possible. This is conventional. If you want to call it easy oil, this is easy oil, okay? And there is a problem with easy oil, because there is a place in the world which is called the strategic energy ellipse, in which there are a handful of countries which hold 70% of conventional oil and gas reserve, and they are concentrated over here. And there are geological reasons for that. This region goes from northern Siberia down to the Persian Gulf and the Red Sea. And I don't need to spend much words to convince you that this is the hottest place on Earth since in the last 70 years. And there are obvious reasons for that. And the obvious reason are these numbers here. But with conventional oil, we have problems, because this is the trend of discoveries versus production. this is the time, and this is the amount of this discovery. And as you can see from here, the golden age of big discoveries has been for conventional oil from the 1930s to the 1980s. And then this stopped. And the green ones are the biggest oil fields ever discovered in the world. And you don't need to be an economist to realize that if the big discoveries are going down and the consumption continues to increase, it's going to be a problem. And the problem is faced presently in this way. We are entering silently, we have entered already silently in the era of extreme fossil fuels, extreme hydrocarbons, extreme oil and gas. So we go deeper and deeper in the ocean to trying to find some new reservoir. We are drilling in frontiers that we didn't dare to drill in the past, like the Arctic. We are trying to exploit other bad, unclean resources like unconventional hydrocarbons or shale oil and gas. I wanted to talk about shale oil and gas, but I don't have time. So these are extremely complicated from the economical, environmental, and technical point of view. So we are, the message for this slide is that we are complicating our life in trying to recover fossil fuels. We are complicating a lot our life because this is all of this is complicated and very expensive. Another point I wanted to address in this part is that we live in an era of great energy wastefulness. This is a very famous flow diagram which shows, I'm sorry, I apologize for the small numbers. These are the primary sources of energy for the United States. And these are the final consumption of the United States. And here you have the way in which the various primary sources are split in the different uses, okay? But the message I wanted to give here is the following, and it is the key message of this slide that would deserve alone a lecture, this slide. But just give me you this hint. At the end, only 40% of the primary energy input in the US is used by the final consumers, by the Americans. 60% is lost. In this lost 60%, there is the second principle of thermodynamics. So this will never be 100. We cannot do it physically, but definitely we can perform better than 40%. And so there is a lot of work to do in terms of energy efficiency. And these are the key hints I wanted to give you in this status part. Now let's see the perspective part, the second part. So the first concept I want to address here is that there is absolutely the need for energy moderation. And to explain you this, I show you an elaboration that I made of some data which are reported here, which report the energy consumption of selected countries per capita per year, primary energy consumption per capita per year of some nations. And this is plotted versus the infant mortality. Infant mortality is a parameter that describes the quality of life of countries. You can choose different parameters like Human Development Index, literacy share, and so on. But the trend will be the same as the one I'm going to show you here. So what is the meaning of this diagram? When you have very low consumption of energy, the countries have a very high infant mortality. The quality of life is poor, basically. And then as long as you increase the energy consumption, the infant mortality decreases because you get the welfare state, very simply. But as you can see, there is a level here, approximately here, beyond which there is no further improvement of the parameter infant mortality, of the decrease of the infant mortality while the energy increases. And Italy, for example, has one of the lowest infant mortality in the world, but and it consumes much less than the United States, Canada, even though this parameter is better in Italy than in Northern America, okay? So there is a point which is approximately here that we can fix at approximately 2.8 ton of oil equivalent of primary energy per year per person, beyond which it is completely stupid to consume more. So the message here is that it is not true that to improve our quality of life we have to increase indefinitely the amount of energy we consume, because this is the message that typically passes. This is completely wrong from the scientific point of view. This is crazy. This is not true. And based on this, I made a further elaboration of data to see where we are and where we could go by mid-century. So at present, the primary energy consumption of the world is at this level. Since we are 7.2 billions, the average consumption is 1.8. So it is below the 2.8 ideal threshold that I set in the previous slide. 1.8. If by 2050 we want to target this ideal 2.8, it can be lower in 30 years because we will get more efficient. But let's take this number, 2.8, the previous one. We will be hopefully 9 billion people by 2050 if there is no catastrophic events, of course. So if you multiply this by this, you get that. So this number is approximately twice as much this one. So the message is, by doubling the energy consumption from here to mid-century, everyone on Earth could, in principle, enjoy an excellent quality of life. So we don't need to multiply by 3, 4, 5, or even 10, because I think sometimes that politicians believe that we have to increase several times. It's just enough to double our energy consumption to give dignity to everybody. Where are we now? China is at 2.2, so even though it is the biggest energy consumers on this planet, it is still below the threshold of dignity. Not to talk about the Western countries. The North American countries are at an acceptable level of consumption, absolutely unacceptable. So they have to be aware of that. And Europe also is at a higher level of consumption. And that's why Europe has decided as the first political entity in the world to decrease the energy consumption by 2020. By 20%. In fact, if you decrease this by 20%, you get almost here. So my back of the envelope calculation are more or less right, okay? So the good news is that Italy is at 2.6. It's already at an ideal level. We can stay even lower than 2.8 because we have part of the country with very good weather condition with lower energy consumption. So we are a very good country in this regard. So it's not true that we are always at the end of the rankings. Okay, in some rankings we are the best, almost the best. That's good news, especially for the youngsters. But there are many countries which are definitely below this level. So, of course, this cannot be imposed. It would be ridiculous. But I think that everyone on Earth should be aware that a balancing of the energy consumption is needed to grant a decent social acceptability of the situation. And if you look at the energy consumption of Ethiopians, now probably you can understand why Ethiopians try to come to Europe, and they make a very difficult trip to Europe to come here, because living at this energy level is terrible. I told you before that to be practical, we have to address two key points, electricity and fuels, if we want to plan our energy future, because this is what we need. So where are we now for the solar electricity? Because we have to go to solar technologies, because most of the renewables are solar. At present, there are three technologies which are relevant on the market. They are wind energy, which is an indirect solar source, photovoltaics, and concentrated solar power. So let's see one by one, where are we now with these technologies. First, wind, the biggest one. The increase of the installed capacity of wind has been impressive in the last 16 years, from 2000. So it increased 25-fold. This is the amount of capacity installed, which is close to half a terawatt. Half a terawatt, it's an impressive number. No one else would bet a penny 10 or 15 years ago that we would reach this level. But I want to tell you another more important number, which is how much electricity is produced by this one. I estimated this number here from a capacity factor of about 21%, which is the average on the world. So presently with the wind, we produce 820 terawatt hours, which is 3.5% of the world electricity demand, which is a huge number, even though it appears small, because 15 years ago it was 0. So it is this number is really, really impressive, and it corresponds to approximately 120 nuclear or coal power plants. And wind is actually replacing progressively the nuclear in the world energy portfolio. This is a clear trend. Photovoltaics. Photovoltaics is a little bit smaller in terms of capacity. The latest data refers to 2014, where about 180 gigawatts of photovoltaics in the world have been deployed. And this corresponds to a production of 200 terawatt hours. Here I assumed a capacity factor of about 11-12%, which is realistic. And so this corresponds to approximately 30 conventional power plants. The good news, again, with Italy, so I'm going to give you a lot of good news about your country, guys, is that Italy has produced, is now at the level of producing 8% of its electricity demand by photovoltaics, which is the highest share in the world. So when you use your electricity, you have to be aware that 8% of what you are using comes from the sunshine. And if you are in a weekend in summer, you have to be aware that almost 100% is produced by sunshine. Okay, so that's a great result of our country. We have to be proud of it. All of these photovoltaics is silicon technology. But what are the alternatives to silicon technologies? This very famous diagram, which is published frequently by the NREL in the US, shows what is over time the increase of efficiency of various cells. But these are, I want to emphasize this, these are research cell efficiency. So typically they are 1 square centimeter cell, okay? This is not something that you can buy, these numbers. However, you have basically 4 technologies, 4 concepts. The multi-junction, which is up here, which can reach almost 50%, but they are not still available on the market. Then you have the crystal silicon, which is the blue lines, which are relatively flat, but you can already buy them, definitely. And then you have the thin film technologies, the green lines, and then you have the new concepts, which are the perovskite, the DSSC, and so on. So what is the situation to be realistic? I know that what I'm going to tell you cannot be extremely well accepted, but it's the reality. Thin film. Thin film now accounts for approximately 5% of the world share of the photovoltaics. Thin film used to be 20% some years ago. So in the last few years, silicon has also cannibalized the thin film sector, which is decreasing its share. What about organic photovoltaics? In that previous diagram, the record efficiency is 11%, and it is the latest result, okay? But I insist, this is a 1 centimeter cell. You will hardly find companies on the market selling reliable organic photovoltaic cells. Essentially, you don't find them, even though some claim it. The SSC, this is the auditorium of the EPFL in Lausanne, but this is a flagship demonstration project. You can also hardly find them on the market. The 1 centimeter cell record is 12%. Here it is definitely much less, okay? And then there is the new solution. Everybody is excited about this, of course. It is the perovskite. And the perovskite is even higher, 15.6 in the 1 centimeter square cell. However, to be realistic, we have to say that there is no competition with crystalline silicon technology in the foreseeable future by these technologies. Why? Because the numbers for silicon are impressive. You are at 19.2. But not on a square centimeter, on 15,000 square centimeters, which is 1.5 meter, a model of 1.5 meter, which can stay on your roof for 40 years. So everyone hopes that this will take up, but still for the mid and probably even long term, there are no big chances to beat silicon. Silicon is the winner. So concentrated solar power. This is an indirect thermal route. This is another technology that has suffered a lot the competition from silicon, because if you read the reports of 5 years ago, the forecast for mid-decade would be 15 gigawatts of this power capacity of this technology. But we are at about 5 gigawatts. There is also one reason for that. Most of the projects 5 years ago, 6 years ago, were plant in Northern Africa, and you know that in Northern Africa something happened in the last few years. So this is for the moment stopped, and most of the plants are located in just two countries, USA and Spain. Now let's come to another much more complicated field, which is solar fuels. Here the perspectives are more complicated because it is absolutely obvious to everyone that it is easy for light to kick an electron across a band of the semiconductor like it does in silicon, but it's much more complicated to start from an impalpable entity like light and make something that you touch, some material, something, stuff, okay, chemicals, fuels. That's extremely complicated. There are already something happening since a long time, the first generation fuels, which require dedicated crops, but has been demonstrated extensively that you can use this approach only in very limited regions of the world, like in Brazil. There it makes sense. In Europe, it won't make sense. Second generation, this is at the very beginning. There is not yet something very established. This uses waste instead of dedicated crops. So from the material point of view and even ethical point of view, this is much better. But what is the situation now of biofuels in the present market? The latest data from BP Statistical Review, and the annual production of biofuels is 70 megaton of oil equivalent, which corresponds to 1.7% of the oil production. So it is a minuscule amount. But what is most important, in my opinion, is that biofuels is not a world story. It is extremely concentrated. Biofuels, it's a Brazilian, US, and German story, and that's it. Most of the biofuels are produced in these three countries, and particularly in America. So they are not widespread as the PV that you find in all of the continents. The biofuels have a problem. There are reasons for that, in my opinion. The biofuels have many feedstocks. You can use sugar and starch crops, lignocellulosic materials, oils, a lot of waste. And this is good because you can adapt biofuels to a specific situation. And this is pretty good for that. And you can have a lot of conversion routes depending on what you prefer, what is best for your situation, pyrolysis, gasification, and so on. And you can make solid, liquid, and gaseous fuels. So that's, in principle, fantastic. But this is also a limitation because photovoltaics and wind are essentially the same device, the same machine, replicated the same all over the world. And so it has reached a critical mass, economic mass, that brings it up to the terawatt scale pretty soon. This is not going to be the case here because you have too many options, which is good on one hand, but is bad on the other hand. And then we have the third generation solar fuels, the artificial photosynthesis. And this is a very important topic of research nowadays. And photochemists are like very much this diagram that probably some of you have already seen, which shows what are the key components of artificial photosynthetic systems. What you need to make in the lab a photosynthetic process that allows you to convert the sunlight into chemicals. Just understanding the secret of nature, not replicating nature. Nature is too complicated. It is even too ineffective because the natural photosynthesis has an average yield of less than 1%. So we need much higher yields. So we have to do something else, looking at the nature to catch the secret. So you need some components, some chemical components which are schematized here. You need an antenna which absorbs sunlight from the sunshine, of course, and this antenna is capable of conveying the excitation energy to a molecule, here a charge separation module, which here there is a photosensitizer, a donor and an acceptor, so you have an electron on one side and a hole on the other side. Then you hopefully need to pool your electrons and holes on two catalysts, because the reaction that you have to make, oxidation of water and reduction of protons, is extremely complicated and requires the catalyst to make it faster. And an additional problem is that this is a 4-electron process, this is a 2-electron process, which is another complication. So you need an antenna, a charge separation module, catalyst, two catalysts, and you need hopefully a membrane. You have to find a membrane in order to separate the two, because you must have the hydrogen separated from oxygen to make it really, really useful. So chemists have been working on these systems on these individual units for a long time. And our group has worked on this part of the story in the last 20 years. And we have studied several artificial photosynthetic systems designed in the lab to try to make viable antenna or charge separating module. Those who are familiar with the literature in the field have probably noticed that in these systems, in these artificial systems, often fullerene is involved. Why? There are specific reasons for that. It is extremely photostable, so you can make your experiment, irradiate it with laser for days and nothing happens. It is extremely stable. It is an excellent electron acceptor, so it is a kind of a electron sponge. And it has photophysical features which make it extremely easy to trace. So it has a combination of properties that make it accessible. And chemists are very able, synthetic chemistry, are able to attach other systems onto it. A lot of beautiful chemistry has been developed in this area. So we have been studying over the years systems like this, in which there is a dendritic structure with the fullerene in the center. So this part here serves as the antenna. So you shine light on the peripheral unit, the energy is conveyed to the fullerene, and once the fullerene is excited, it's capable of accepting one electron coming from this part of the molecule. This is a small example. And we have studied several of these examples with metal complexes, porphyrines, and other organic systems showing that there is an electron transfer going to the fullerene. And we have also studied recently a more complicated example in collaboration with Davide Bonifazi, who is right here. Ciao Davide, I haven't seen you before. In which you have a fullerene type system, an antenna type system like here. So you can shine light here, the energy goes to the fullerene. Here the fullerene can receive an electron from that and that, but we demonstrated that only the phenothiazine is capable of doing so. Instead, ferrocene quenches by energy transfer. And let me just give you another example, which is probably the most sophisticated one we have investigated. I just give a cartoon in which there is an extra-substituted fullerene with 12 porphyrin on the external part, and an incoming fullerene which acts as an electron acceptor, which attached to the porphyrin in a supramolecular way. So this is a model supramolecular photosynthetic antenna with the porphyrin and charge separating unit thanks to the fullerene. And as chemists, how do we see these electrons that move here and there? What we do? We just make laser spectroscopy and we see we trace the fingerprints of cations and anions of the species which are involved, and then we detect the lifetime of the species. This is the homogeneous approach, okay? But most of the work now is addressed in working in a system based on semiconducting system, in solid system. And everything started, the so-called photoelectrochemical route. Everything started in the early 1970s, during the first oil crisis. Two Japanese researchers published a very nice paper on Nature, and they said they could use a single material, titanium dioxide, which is capable of absorbing light, creating a charge separation on it. They wanted to show that this could oxidize water and reduce protons, and having also catalytic activity, so a material that does everything. Actually, this turned out to be at the end more complicated than expected at that time, and after 40 years, this magic material doing everything from light absorption to catalytic activity and to everything has not been found, basically. So chemists have been trying to find other alternative solutions. This is just a schematic concept. And the first idea was to attach a catalyst on the semiconducting, so in order to decouple the catalytic activity. And this occupied several scientists for many, many years. And then the next step was to use two different materials, semiconducting materials. One on which there is the oxidation on water, and on the other, the reduction of the proton. And this is, the two materials are the red and the green on the back, okay? And they have to be connected electrically. The connection can be made in different ways, without wires. In this case, it's a monolithic system, or with wires. There are several variants of this concept. The key concept here is that you have two materials doing the two things. And it is easier, and several systems have been found to work. The next step is to take out the light absorbing capability of your system and to make something like this. So you take something which can be a photovoltaic cell. This has been done frequently. And so you have just the production of your electron and holes that you inject onto electrodes. And the electrodes are no longer photoelectrodes like here. They just are electrodes. And then you have your reaction running. And then there is a further step, which is actually historically the oldest one, which that you decouple completely the production of electricity and you take it from the grid, hopefully made by sunshine with photovoltaics. And then you inject your electron and holes. And this is essentially electrolysis. Okay? So these are the main concepts. And a lot of researchers have been working on this. However, very recently, I decided to make a provocative calculation that I'm going to propose you. I hope that someone will not be too much disappointed. And because I asked it to myself, is it reasonable to make a hypothetical water splitting roof? I mean, you can buy now your photovoltaic roof and produce electricity for your yearly energy need. It covers what you need for 1 year, your 17 square meter approximately photovoltaic system. What about a theoretical photovoltaic, water splitting roof? So I will give you some calculation, but just catch the key message. I don't want to make you too bored about that. So the basic assumption is that you have a current density of 10 milliamps per square centimeter, which corresponds at the current level of development of materials at a 10% solar to fuel efficiency, under one sun. So if I target half a kilogram of hydrogen, this corresponds to 250 moles. And the current needed for the target, if this is the Faraday constant, is approximately 48 million coulomb. In 8 hours, a device operating at this current density will pass 288 coulomb per square centimeter. If you make the ratio between these two numbers, you obtain the surface that you need. So a device working with this current density would be large 16.8 square meters, and this device would produce your half kilogram of hydrogen in 8 hours under one sun. So is it a big amount or not? Let's look at it. Let's extend the calculation across the year, in 1 year. In 1 year, you have to assume one sun on the roof, not always. Now, there is no sunshine. And in northern Italy, you can approximate roughly 1,300 hours per year of sun, of full sun. In your hypothetical panel of 17 square meters would produce approximately 80 kilograms of hydrogen per year. Is it a big amount or not? I don't know. You can make several comparisons. I decided to make this. You have approximately the production of, the consumption in one household, presently, this is what you do, guys, 800 kilograms of natural gas, of methane in your house. But the heating value in mass term is higher of hydrogen. So in short, the bottom line of this calculation is that a water splitting system, 10% efficient, over a surface of about 17 square meter, no idea how to make it. No one knows how to make it. A 17 square meter water splitting devices, normally they are that big, okay, and they last minutes, maybe hours, would produce 195 kilograms of methane equivalent, which is less than 1/4 of the annual consumption of an Italian family. I leave you the consideration. I could make further comments on this, but I leave you to ponder, the idea to ponder this number if it is good or bad. For me, it's not that good. So now I come to the last part, the bottlenecks, which is probably the most important part I want to tell you today. The first bottleneck that we have is the material constraint. In one of the first slides, I showed you that we have enough energy, enough renewable energy, good news. But we have another problem. As addressed recently by the American Chemical Society, we live in a world which has a specific periodic table. A distribution of element, availability of element on Earth is described by certain number. In other places of the universe is different, but we have to make our calculation on this planet here. And some of these elements are increasingly endangered in terms of availability. And here the concept is very simple, but challenging. To use solar energy, we need obviously photons. Obviously. And photons are an overabundant extraterrestrial input. We don't have to care about this planet on light. We have to rely on something coming from 150 million kilometers away. And we have plenty of it. That's great news. However, we need also atoms. We need chemical elements. Why we need so? Because solar light as such is almost useless, apart from heating a little bit. You need converters and accumulators of solar energy, which are made of terrestrial material. So in this regard, renewables are not that different compared to oil, because you have to dig this material in the Earth's crust. And you have to be honest with ourselves and also with the general public that also renewables require something that has to be found on this planet. And this is typically overlooked. And it seems that nature enjoys to joke with us, because all of the renewable and efficient energy technologies require these damn rare elements. You require rare earths for the permanent magnets in the wind turbines. You need them for your hybrid car, for the thin film. And you need them also for lighting. These are the elements which are used in the phosphors of the lighting sources. And just about this, I want to use very few minutes to show something why I got interested in that, because this came from our research interest. This is the classical point source, the lamp, but as you are certainly aware, scientists are also concentrating in using flat diffuse light sources, like making panels like this, but they are emitting by themselves. And if you go now, you listen every day on the TV that there are advertisements of the first OLED TVs, which cost like hell. And one of the reasons why is that the deposition method to make OLED devices, which imply an emitting material here, several emitting materials here, and ancillary layers to allow the injection of the positive and negative charge on the two sides, are extremely expensive from the economic and energetic point of view. And moreover, you require neutral emitters for OLED, which are relatively rare to make, especially if you target triplet emitters. And you need this multi-layer structure, and you need a lot of energy to the solid deposition of these materials. So scientists have been looking for alternatives, and one of the alternatives is to use light-emitting electrochemical cells, which are simpler devices which use charged emitter, but they can be made by solution processes. I don't want to enter into too many details. I don't want to bother you on that. But we have been working on this technology. You cannot buy LEC devices in the shop. You can buy OLED, but you cannot buy OLED. They are only demonstrators. So the research has started later. The typical materials that are used for LECs are iridium complexes. And we have been studying iridium complexes of this sort for a long time, and the basic design concept is the following. You need 2 cyclometalating ligand and 1 ancillary ligand. So you have 2 minus ligand, the iridium is 3 plus, overall you have 1 plus, because you need a charged emitter. And the good news about iridium is that by changing the ligand, you can design your compounds in order to let it emit all across the visible region from violet down to the red. And this can be done by ligand design, even though getting blue emitters is challenging. And we have demonstrated a few years ago in a European project that it is possible to make these kind of devices. But just about the material constraint, there is a problem. The problem is that iridium is the rarest element on the Earth's crust. You can find it only where asteroids hit the Earth. And one big asteroid hit South Africa, where South Africa is now, millions of years ago. And there you can find almost all of the iridium. And so it is probably not realistic to illuminate the world with iridium. And we have been looking for alternatives since a long time. And we have been studying copper complexes as possible alternatives. And a few years ago, we suggested to look at this part of the periodic table here, at the so-called D10 metal complexes with full d orbitals, and particularly monocathionic and dicathionic elements of these metals. But, as you can see, 2 of them are toxic, mercury and cadmium. 2 are very expensive and or rare, like silver and gold. And so only copper and zinc are left. So copper is one of the main choices in this direction. So can we make copper complexes usable as triplet emitters in electroluminescent devices? To make a very long story short, this is 15 years of research. We have demonstrated over the years that copper can change its coordination environment, and you can go from red to green to blue. But the intensity and the stability of these compounds is not comparable to iridium. So the very bottom line is that iridium still outperforms copper in electroluminescent devices, and we enjoyed and we had a lot of fun in changing ligands and finding the tunability of the emission. And with copper, we tried to make the same. We definitely found much more exciting chemical structure than these boring complexes like this one. And they do emit, but they are not comparably stable and tunable in devices. So we found our material trap. We're trying to find alternatives, but still iridium is the king. So I want to tell you about another bigger material trap, much bigger material trap, which is about transportation. Transportation is one of the big part of the energy conundrum, because everyone has a car in the developed world, and even not only. So if you want to change from gasoline to something else, you have two options, biofuels and electricity. Which is the best route? Recently, a very interesting paper appeared which calculated the sun-to-wheel efficiency. So how much of the energy of the photons goes to the wheels of your car. That's a very important concept. And if you go through the biofuel route in America using bioethanol, the conversion is miserable, 0.03%. If you go through the battery route to the electric route, the efficiency is much higher. I don't tell you how many square meters of this planet you need to make this compared to that, because that would be even more depressing. But it's pretty clear anyway that this is the best solution. So I asked to myself the following question recently. Is it realistic? Is it realistic to switch from fuel cars to electricity cars? Or should we cripple the entire electricity system of a country if everyone has an electric car? So I made a simple calculation to try to answer to this. And I took as a reference the Tesla car. Probably some of you know the Tesla. Tesla is the most luxurious electric car in the world. It's like a Maserati or a Jaguar, okay? And so I took this number to be abundant, so no one can criticize this calculation. So this car consumes 0.18 kilowatt-hour per kilometer. So the average mileage in Italy is 12,000 kilometers, and there are 37 million cars. So if all the Italians would drive a Tesla, how much electricity would we consume? Very easy to calculate, 80 terawatt-hours. Is it a big amount or is it a small amount? It is a totally reasonable amount. Because Italy already produces over 120 terawatt-hours by only renewables only. So by increasing 60% of renewable production in Italy, every Italian could drive a Tesla car without destroying the Italian electric system, okay? I was surprised when I made this calculation, I confess you, but if you think that more than 95% of the time cars are stupid pieces of iron, glass, plastic, rubber, stopped in stupid parking lots or in stupid garages, which are totally useless, okay? More than 95%. That's why this number is not that big. But there is another problem. I'm talking about material constraint. What about lithium? Chemists know why lithium is ideal for batteries. It is the lightest solid metal with the highest electrochemical potential. So lithium is probably the best choice. This is a limit that we have. Probably it is. And the battery of the Terza is in the basis of the chassis. So I made another small calculation. The cars sold per year worldwide are 70 millions all over the world. One electric car requires about 10 kilograms of lithium per car. So if all of the cars would be produced electric with the present technology, we would need 700,000 tons of lithium. What is the current lithium production in the world? Less than 25, more than 25, less than this value, 20 times. So in this case, we do have a problem. So we have a material constraint. And lithium is also needed for other uses, of course. And one day, maybe it would be used for nuclear fusion, who knows, to make tritium. So we have one option. The first option is the recycling option. But the recycling option, we are still at a sort of stone age, because this is the rate of recycling of metals, and all the pink spots are the elements, the metals, which are not recycled at all, and lithium is one of them. So this is not an option. So someone may argue we have also the replacement option. But recently a very interesting, but on one hand even depressing paper was published on PNAS, proposing what is the periodic table of substitute performance of metals. You have a color scale here. The blue elements are those which have exemplary substitutes for all major uses. The red ones are those who have no substituents for all major uses. But unfortunately, in this table, there are a lot of red spots, orange, and definitely no blue spots. So the possibility of replacing often is not yet possible. And finally, this is the very final concept I want to present today. It is the other constraint. It is the energy return constraint. Because we have to be aware that we have also the problem of the energy trap, which is described by the concept of energy return on energy invested, EROI. This is a parameter that has not been, it is not estimated with universal protocols yet, but it's something that we have to start investigating deeply. What is the concept? The concept is that it takes energy to get usable energy. So if this is your favorite gas station, everyone can understand that to get your gasoline available in the tank, coming from an oil field in another continent typically, possibly in the middle of the ocean, requires a lot of energy investment in terms of transportation and refining and so on and so forth. So you have to know what you get out of it and what was the energy investment to get it. And the ratio between these two numbers is the EROI. The EROI differs from the net energy, which is the difference between these two parameters. And there is a mathematical relationship between the two, which is nonlinear, which is this one. So I put this on this diagram. This is the EROI, and this is the net energy. Conventional oil and gas, the one that we have used so far, has a very high EROI. You invest 1 unit of energy and you get in return 60, 70, 80, a lot of energy. This was an energy bonanza that we enjoyed for decades. But this is not easy to, as I said at the beginning, this is no longer possible. This is an incredible era which is poised to end. And this is the same for hydro. But the interesting point of this diagram is that it has this inflection here. So there is a point which we can call the EROI cliff, beyond which the net energy that you get back is much less than what you have invested. And it is important to note that if you look at the numbers of EROI available for wind and PV, we have to note that the solar electricity is above the cliff. And this is good news. So solar electricity is at an advanced level. It's not here, but it's not below the cliff. Instead, biofuels, unfortunately, they are absolutely below the biofuels threshold. And this is a very important concept for societal consequences. Because so far we have enjoyed an energy system which is schematically depictable in this way. We had energy sources, and we needed to invest a limited amount, to reinvest a limited amount of energy to get it back and to keep the machine running. And then you had a lot of energy to spare to satisfy the primary needs, to make discretionary activities like attending lectures, as you are doing right now, or even for growth. Growth means infrastructures, for example. However, when this gray energy, the amount that you have to reinvest to get the machine working is increasing, you have to start eroding the discretionary and the growth activities, as long as you believe that primary energy cannot be touched. And then you can get to a time in which what is spare is absolutely left, and you have only energy to satisfy your primary needs. And you can even go to a period, very dangerous one, in which even the energy that you get is not even necessary enough to satisfy the primary needs. And it is obvious that a world with EROI, with a declining EROI, is a world which is going to have several societal and problems. So this is almost the conclusion of my talk. I want to sum up and give some key points. The individual energy consumption of most affluent countries is beyond any reasonable level. And this has become a threat to social stability in the Western world and in the affluent world. We know it and we see it every day on TV. The golden age of fossil fuels was great, but cannot be replicated. Among others, it has a uniquely high EROI, a uniquely high return of energy. The limiting reactant in the complex energy equation is not light, but it's atoms. And technological choices should be driven by this fact. So we should decide what to do and what not to do looking at this. Solar electricity is established and with substantial advantages. In terms of time, it is a 60-year-old technology, the silicon. Materials advance, there are no particular problems regarding the materials availability of this technology, and EROI, which is acceptable. Storage remains an issue, as I try to point out. Solar biofuels, they are still at a very early stage on all aspects. We are still in a sort of stone age also for solar fuels. And the biggest research effort is needed here because we do need fuels, always. So we are facing a daunting challenge. In the next decades, we have to expand the energy availability because we are now 7 billion, but we are going to be 9 billion by mid-century. While we expand the energy availability, we have to change the primary energy basis from fossils to renewables. And this is a terrible challenge, very complicated, technically and socially and so on. And in this process, we might even experience the limit of economic expansion, as I tried to address in the last slide. However, unexpected happenings cannot be excluded, and possibly these happenings can be positive. I just want to conclude with one final slide to give the final message. The final message is that on this planet we have limits. And a nice photo of these limits is this picture here. These are the cleaning operations on the Louisiana coast after the disaster of the Deepwater Horizon 6 years ago. As you can see from this picture here, there is no spatial robot or spatial machine capable of cleaning up the Louisiana marshes. The only machine that you have is your arms, and you wear gloves, and you go there, and meter by meter you clean it up. So the message I want to give to the youngsters is that science and technology are not the solution to all of our problems. First, because we have limits. Second, because when human stupidity goes beyond any reasonable level, there is no remedy to this. And I thank you very much for your attention. Per gli italiani, dico in italiano, da qualche tempo dirigo questa rivista Sapere dove trattiamo anche di questi problemi, quindi potete andare a vedere il nostro sito e eventualmente ad abbonarvi. Fatto lo spot finale, perché uno spot non si nega a nessuno, no?
L'hai fatto benissimo. So thank you very much for this very clear picture. You said many important messages with very much clarity. Thank you very much. So the floor is open for questions and comments. Yes, Roberto.
What is the situation about the creation of other fuels with respect to biofuels with solar energy? So I'm referring to converting CO2 to methane or other fuels. So it will be also important, I think, for the production, for the usage for transportation, for example, because you don't have to change the engine.
Yeah, this is a very important question because I talked only about the water splitting. And as probably it was clear, I'm not very convinced that making hydrogen with solar energy at the very end can be a solution, at least with photochemical and photoelectrochemical systems. Probably electrolysis is the best. But carbon dioxide, as you point out, is the different story, because carbon dioxide is a problem. So we have the well-known problem of carbon dioxide. So using sunshine to convert carbon dioxide in methanol, for example, is a very important point instead. Even though, in principle, it can make less sense from the energetic, economic point of view, since it is a problem, this must be addressed anyhow. The problem is that it is much more complicated chemically, catalytically, photochemically, to convert carbon dioxide in methane or in other molecules, like even carbon monoxide, and then to make syngas to go through the Fischer-Tropsch. That makes, according to me, absolutely sense, but it is even more complicated than water splitting. This is the key problem. So I think that it has to be absolutely addressed, it has to be absolutely pursued, but we have to be aware that we are still lagging even more behind in terms of development of research and technology for carbon dioxide reduction. No, I mean, it is the only chance we have. There are no other options, because we must do it. The problem is that we are lagging behind. So so to answer to you, we must do it, no way. I'm sure that several of these youngsters will work in this field, because this is one of the futures, in my opinion. What scares me is that we are late on several points, and there is also an historical reason for that. In the 1970s, there was the first oil crisis. I was a kid. I was 7 years old when I remember that there were the Sunday the cars were not allowed to be driven on the streets, and people went only by bike or by skates and so on. At that period, there was a spike in energy research for solar energy conversion. Then everything stopped in the 1980s, because the market and the economy and the world went to a situation by which the oil costed less than $10 per barrel. So it was absolutely uninteresting for scientists, and you couldn't get any single fund to make research in this area because of that situation. So we lost 30 years, because suddenly, at the beginning of the 2000 years, people realized that we have a problem, because then the oil jumped back to 100 euro per barrel, dollars per barrel. And so we lost 30 years. These 30 years has been a disaster, in my opinion, looking in retrospect. So we are paying this bad choice. This is the typical indication that if you leave everything to the market, it will not work. This is a clear example. So in an ideal world, at that period, in the early 80s, the government should have decided to say, okay, let's fund solar energy, because this period will not last forever. This was not done. So the future is absolutely recycling. There is no doubt about that. No doubt.
Does the industry make any effort to make recycling easier? For instance, the electronic circuits are made of many difficult to get materials, for instance, gallium or whatever. If one starts with a convenient design, maybe it would be possible to improve recycling. Is that done or not?
This has not been done for many decades, and then they start planning materials not only for the end life of the user, but for the end life of the device itself. So now, especially Europe is leading the way in this, to making devices which are designed in such a way that can be disassembled in a rational way and then can be recycled in a rational way. And also in this, there is a lot of work to do for the young people here in the future.
There are many engineers here.
Yes,
I hope you really listen to this.
you have to do it, because now we are discarding all the electronic devices that were not planned for this activity. So the technologies that are used to make this recovery are extremely harsh. the less harsh technology use ionic liquids, and there are chemists that know that ionic liquids are not the most the easy to handle materials that you can have for a variety of reasons. But this is the gentlest way you can treat these materials. So also in this there is a lot of work to do, and I insist, as in the previous one, that we lost 30 years in realizing that this was needed, because there was the idea that this planet was a plentiful reserve of everything. This is not the case, unfortunately. I think that we have to start. I tell you another point. I am 100% sure that the reason why Saudi Arabia decided to bring down the price of oil to 30 euro per barrel is not only because they hate Iranians, they hate US, and they hate the shale oil. This is what you read on the newspapers. It is because they are terrified by the electric car. They don't want it to lift. This, my opinion, was confirmed by an oil guy that I met at a conference in Florence last Saturday. We didn't agree on anything with this guy, but he told me, you are right. I tell you, Arabians are terrified by the electric car. That's why they bring the price so low. So in my opinion, there is no other alternative. Of course, now you use 10 kilo of lithium, you make the calculation, probably one day you can use less, definitely, you can improve in this. We have plenty of possibilities. Not everyone has to use a Tesla, of course, hopefully. And so this is another opportunity. The good news is that lithium instead is easy to recycle because you have a big quantity in the battery, so it is easier to recover. It is much more complicated to recover indium from this screen because there is a nanometer foil, and that's extremely challenging, and just about the previous question. So in my opinion, is that electric is the future. I am absolutely aware of that. Of course, there could be also progress in other batteries, like sodium batteries. But sodium has a low electrochemical potential. It is 3 times heavier than lithium, even though it is just below in the periodic table. So it is not at the same level of advancement compared to lithium batteries. But in my opinion, the only future for transportation is electric. There is I have no doubt about that. Prego. What can I tell you? That's the most complicated question that I got tonight. I am active with other colleagues in Italy and in Europe to try to speak with politicians. I participated to meetings at the European Parliament, not at the national parliament, but from time to time some politicians try to contact me or other colleagues which are sensitive to this problem. Definitely, what is driving the choices for us Italians is Europe. So without the European drive, we would not be at that level in photovoltaics and so on and so forth. Okay. So Europe is, at least so far, has been aware of that, has been driving the rest of the world, because after all, the Paris Agreement has been driven, if you look back, by Europe, that finally tried and succeeded to convince other countries to go along this route. And now it is impressive, but probably we don't have realized the importance of this. There are several mechanisms that have to be implemented for the Paris Agreement, but the fact that all of the governments on this planet have recognized that this is a problem, it is a very, very good point, absolutely. Then it will take time. What again scares me, I'm optimistic that on the long run, even the politicians will take up. The problem with politics is that, first, the short-term vision. And second is that the world is running so fast that making legislation Instead, it's a long process, and these two machines are running at two different speeds, and this is another problem. This is also something that we try to convey to the politicians. So, to make a long story short, I think that each of us has to devote part of its time to try to convince the general public, from the elementary school to the universities, to our students, to everyone, to politicians, because at the very end they take the decision, that this is the most important problem we are going to face. If we are not able to resolve this problem, our civilization will pass a very tough period of time.
Okay, so we'll take two more questions, and I'm really bleeding inside because I'm giving up. I'm sorry. I already have two.
Okay.
And then afterwards, though, there is some refreshments back there, and you can talk to Nicola maybe directly there. But at 7:15 we have to be out of here, so we definitely need to.
Yes. Well, I have another political question, which goes back to the very beginning of your lecture, and is that 2.8 figure. Which would be reasonable. I think it's easier for those who are above that figure to go to 2.8 than for those countries that are below the 2.8 to reach the 2.8 or whatever it is, which of course would be desirable in a global picture. So, what are the technological issues and the political issues? But what technologies one could think of those that you have shown would be more appropriate to overcome the technological divide that this one half of the world has? Because you don't want to reduce the consumption in one half, but you also want to increase the consumption in the other half.
What I can tell you is my personal experience that I had recently 2 months ago, visiting a remote village in eastern Zimbabwe, close to the border with Mozambique. It is really astonishing to us to see that there are places in which by night it's dark. It's dark. Dark is dark. So I realized finally what is dark, because I was born in 1966 and I was born under light, okay? And what I also realized is that in that specific case, they have the infrastructure. They have the electric line going to there, but it's empty of electrons. So they are not receiving this. One good point regarding the energy transition is the fact that we are moving towards electricity, and we should move, and we are moving towards an electricity powered world more and more. So that 25% I showed is becoming 30, and then it will become, in the US it is already 40. So, and the good news is that the best technologies are electric, already developed, as I showed in the last slides. And these technologies can be implemented out of a grid. So we have to take advantage of this fortunate situation in which you have a technology well developed, cheaper and cheaper, and that can be deployed at the local level. I have really realized that for them, having a solar panel, even without batteries, having a solar panel running the fridge to keep the meat and the food safe is a big advantage. And you can do it in a disconnected way without attaching to the grid. Because in our modern Western world, we have an energy infrastructure, which is essentially what you say. It is difficult for them because they don't have even the infrastructure. But with the new technologies, you can jump the infrastructure. And what surprised me is that what you have in those even remote areas, very poor areas, some of the poorest areas in the world, they have the mobile phone. That damn mobile phone is always on. I tried with my one, and I always have at the line, even in a remote place, 3 hours far from the closest asphalted road. This is another example of this of a technology that doesn't require a solid infrastructure. So they jumped the telephone line. They don't need the telephone line. So they jump directly to the mobile. So I guess that they can jump directly to these technologies, which will allow them to be faster than we did in the past to get our energy available. I'm not sure this is the solution, but the situation is better, even because I have to give also some good perspectives, I mean some positive perspectives. And I think this one is one of the positive ones.
Something also we have to discuss about how it is possible to integrate at an early stage when you are developing this kind of technical question solution, integrate also the vision of the societal organization that makes sense according to the technical solution and vice versa. Which particular technical solution fits a particular kind of social organization. Because to me, this is a big question. The two sides of the issue are always totally mostly independent of each other. First, the technical efficiency, sensitivity of the solution, and then societal application, and generally in a very, this is highly refined, but the societal application is very simplified. You basically take society as it is organized now, and you extend it across time, as if it goes on forever in that same way. But it is really a my question is how it is possible to integrate the efforts in a very early stage.
I can give you this example, which came to my mind recently. The landscape, since you talk about society, landscape. So the renewable energies, whatever will happen, are there to stay. So in the future, our human civilization will be powered by renewables on the long term. So we have to integrate this on the landscape. And we are not yet mature to do so. Every time there is discussion about the installation, especially in the West, especially in Italy, because we have high density of population, there is the discussion about where to put these plants. This is not done in a rational way. So we are at the very early stage of integrating renewables in our society, and this is just an example. Because there is no legislation clear at the European level, for example, every country does individually. So even though Europe is ahead of anyone else in the world, we are still lagging behind on this. So this is a clear example of what you say. Society is not yet ready to do it. So we have to be aware that the integration of renewables in the landscape will be the key driver of future planning of our cities and our land and our countryside. But this is not yet clear. Another point regarding transportation that you mentioned, whatever you do, just to also to take up your question before, whatever you do, there is no doubt that you have to make lighter vehicles. You have to make absolutely lighter vehicles because they are too heavy now. So even in this regard, you have to convince people that their car in the future will be probably less sexy than the present one. I don't know. There is a lot of work to do, and that's why I try to convince people and to be an advocate for the professionals like we are, to be advocate of this and to try to explain this as much as possible. It is a very tough endeavor, but we have to do it. We have no choice, because you are right. I mean, society is not yet ready to change the landscape and to change their car and to change several things, but they have to do it. There is no alternative. What we have to be successful, and I'm pretty convinced of that, we have to demonstrate and to convince them that will not be a worse world than it is now. It will be much probably a better world than it is now. But we have to be very convincing and very brave to do so.
So just two closing words before you can dig into the food and we thank our speaker again. I just wanted to thank you all for being here. I see a very diverse audience and I think this is a success. Those of you who are standing probably don't think this is a success because you didn't have a chair. And this is definitely my fault, but it's not my fault because I really wanted this to be a packed room and a very cozy environment. And those of you who are standing, maybe not those of you, but many people forgot to register. And this is why you're standing, or some people are standing, because this was a registration-based event. So anyway, I just wanted to say one thing about this lecture series. As I already said, this is part of a series of initiatives on energy and environment. And we're really thankful that we had Nicola today, but we will have more, so I hope you can be part of that. We will have more of these initiatives, not only on the education side, but also on the research side. We're trying to really pull together all the research activities and the education activities on this university that are doing environment and energy. So check in with me if you're interested. Before we close, I just wanted to thank, well, the university staff and admin who really helped in this event, and especially Alessandro Massipavan, who's been really doing a lot of these things. This being said, the only thing that is left is to thank our speaker once again.